Okay, this video will look at the one-star practice questions for Chapter 13. Several of these are actually explaining type questions, so they will we'll talk our way through them, so you'll have to take notes as we go through. So first question, question 11, what happens to the speed of a pulse in a Slinky spring if it is stretched? So let's draw a couple of springs. First off, let's draw our Slinky as if we're just holding it, and now let's do the same thing, but let's stretch it out a bit more. Let's see, there was 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Let's just twist it off a bit. So here's before, and here is after. So we've got the same total length of material, but now instead we've got it that it is stretching a bit further. So we might say that is distance of x, and that is distance of x plus some extra value y. Now, a couple of ways we can think about this. If we think about this from a particle point of view, well, when we make this end go up, then it pulls on the next bit, which pulls on the next bit, and so on, and the wave eventually passes its way down. Now, how far apart those particles are stretched when we look at it like this really doesn't matter. So it's going to pull at the same rate, and since it's travelling a further distance, it will end up moving faster. The fact that it's got longer to go doesn't actually matter, because we're just talking about velocity, and velocity in this case talks about, well, what is it relative to? It's relative to the ground, or whatever sort of stationary position we think about. So if it's moving through the particles a certain v here, it'll have the same particle v here, but relative to the actual ground, it'll end up going at a faster speed. So v will, I don't know what I was writing there, v will increase. So hopefully that clarifies why this would actually go up. The other reason is that because we're increasing the tension within the material as well, if we were to say just go, well, let's keep it the same distance, but instead we'll only use like 4 coils instead of 5 coils, we've increased the tension, and so it will flow through there a bit faster. That's more of a material properties point of view. Okay, let's head on to question 12. Question 12 reads, explain the difference between a longitudinal and a transverse wave. Now, you'll have a definition. You can go back up through your chapter textbook to have a look at that, but things that you would talk about, well, direction of motion versus oscillation. Remember that for a transverse it is perpendicular, for a longitudinal it is parallel. We could talk about what the wave crests and troughs are actually meeting. So for example, one is about compression and expansion, while the other is about amplitude from mean. And if we wanted to get into some examples, we could talk about light versus sound related to a medium. Remember, light, while it is a transverse wave, does not require a medium, while sound, being longitudinal, and it does require a medium. So you can put those points together however you wish to. Those sort of questions are very open-ended. Okay, question 13. A dinghy anchored in the ocean is seen to bob up and down as the wave passes. So, as we just mentioned, direction of oscillation being perpendicular to the direction of motion, because waves are moving through the medium, but the boat is going up and down. This must mean it is a transverse wave. Alright, how do we know that? Oh, well, we just explained why we know this, because of up and down versus direction of motion. Okay, what physical feature of the wave indicates the energy the wave possesses? So if we think about the relationship between energy and waves, there's a couple of answers here. One, we could use our E equals HF relationship and state, okay, well, the more frequent the wave is, the more energy it must have. So that's talking about energy in direction of motion. So E in direction of motion. But what about the size of the wave? Does that matter? Think about if you're trying to move your arm up and down. If you move your arm up and down a small amount, it uses less energy than if you move your arm up and down a large amount. So the amplitude should matter as well. We find that it actually does. Now, we've just talked about this formula here is talking about energy predominantly in light, hence that Planck's constant in there. So it certainly still means that the faster the wave, a water wave, is moving, that there is more energy, but it's also the size of it, because if we were to have two waves with the same wave, that was a terrible wave, sorry. If we have two waves with the same wavelength, but different amplitudes, well, if it's the same wavelength and they've got the same frequency, then they've got the same velocity. So the time it takes to go from crest to trough, let's say, is 1 second. Here, crest to trough is 1 second. That means then it's got to travel further, and because the distance is further, well, velocity equals distance over time. If time is the same but distance is bigger, then velocity must be bigger. And if velocity is bigger, if we think about our formula for kinetic energy, half mv squared, if the wave has the same wavelength and the same frequency as another wave, but it's got a bigger amplitude, it must have a faster velocity, and hence will have higher kinetic energy as it moves. So we could say that both amplitude and frequency, so therefore amp and frequency, we'll just abbreviate it there, is proportional to energy. Okay. Let's head on to question 14. Name a particular type of wave where the particles move at A, right angles to the direction of propagation, B, in the same direction as the wave is moving. So now we have to think, well, what right angles to the direction of propagation? What sort of wave is that? We've got two types, so 50-50 chance if you're not certain. And then after that, come up with an example. So right angles, that means it's transverse. Okay. And we've talked about some examples, but the common example we use is light, okay, because it's transverse. Second one, well, now we've got the opposite, so we must be dealing with a longitudinal wave, which means sound is always a good example for a longitudinal wave. There are a couple of others: Mexican waves, ocean waves, radio or X-rays or gamma waves. All these are examples of light, so those will just fall into that same category. But if you have a Google, I'm sure you can find maybe some novel examples. Okay, so here, describe what is meant by the wavelength of a wave in relation to a longitudinal wave. Now, transverse waves are easy. We can just say, oh yeah, it's the distance between two crests, or the distance between two troughs, or the distance of one repetition. Now that last definition is the most useful, the distance of one repetition. So if we draw a longitudinal wave, and this is always tricky, so what I'm going to do is let's start off with some lines to show compression and shrink it, then expand it, then shrink it, then expand it. So we've got this pattern of high density, high density, high density, and this area of low density, low density, low density. So let's put an L for low and a H for high. So the wavelength in this case is the distance between the middle of our high density areas, or the distance between our low density areas. Okay, again, we can say it's the distance between crests and troughs, or the distance for one repetition, so from the start of this compression to the start of the next set of compressions. But no, it's still the same feature, it's just trickier to draw, so you don't tend to see a lot of pictures of it. Alright, question 16, state the wave equation indicating the meaning of the symbols used. Well, let's state the wave equation. V equals F lambda. So what do each of these things mean? And we can go V for velocity, how fast the wave moves, F for frequency, how frequently the wave oscillates in time, and in lambda, the distance between wave crests, or distance between wave troughs, or the distance of one repetition, as a definition of a wavelength. We can throw some units in there, so units are always good to mention. So let's list those off. So name, meanings, and units. With meaning examples can also be good to help extend those sort of questions. Okay, but there's nothing too complicated there. You're mostly being told to go back to your theory. Okay, question 17. Now we're getting into a bit of math here. 2 students shaking a slinky create 10 waves in 5 seconds. The wavelength of the waves is 50 centimeters. What is frequency, period, and speed? And we'll come to that in a second. So let's start listing things off there. So 2 students shaking a slinky create 10 waves in 5 seconds. So let's reread that. We could say that is 10 waves per 5 seconds. And we see that per second wording popping up that we saw back in question 1. So per second, we're talking about a frequency. So we need to work out, well, how many waves happen in 1 second? And we can see that, well, F in this case would be equal to 10 divided by 5, or 2 hertz. Now we're told that the wavelength is 50 centimeters. Lambda equals 0.5 meters. Remember, always convert to SI units. It just makes things a bit simpler for yourselves. And V would equal F lambda. We have been asked to find speed, I believe. Yes, speed is one of the things. We've just identified frequency, so that's part of A. We need to find speed or velocity, so let's substitute that. 2 times 0.5 equals 1 meter per second. And we also need to find the period. And remember from the earlier examples, period equals 1 over F equals 1 over 2 equals 0.5 seconds. And remember your SI units. Now the points are a little bit hard to see on previous questions, so let's just make those a bit bigger. Alright, now 17b. We've got to think a little bit of prediction here. If the wave was shaken at a higher frequency, 1, what characteristics of the wave would change? So if we shake it faster, what happens? Well, let's pretend that, start off with that velocity doesn't move. If we have a look at our equation here, we see that V equals F lambda. So if this goes up, if this doesn't change, that has to go down. Okay, we can think of it like, so 2 times 0.5 is 1, 4 times 0.25 would be 1, so that would go up to 4, that would go down to 0.25. So wavelength will reduce. Okay, and that's all. If the physical properties of our medium doesn't change, then our velocity will not change. The velocity will be altered if the tension was changed, or if the heaviness of it was changed. Like we increase the mass, but not the velocity. So the second part, what characteristic would remain the same? Well, that's going to be velocity. Now obviously frequency would go up because they've said that the frequency goes up. I think that's fairly trivial, but the textbook does say, state both. But if frequency has been increased, although it does, it said a shake at a greater frequency, I still think that's a bit of a silly thing to bother getting a student to note down as well. Okay. The wavelength's the interesting one. Okay, part C, how can the speed of the wave be changed? So a couple of things I just mentioned before. So when we're changing properties of a wave, or the speed of a wave, we need to change its properties. So we need to mess around with the physical properties that it's moving through. That, like when light goes from a vacuum into diamond, it slows down quite a lot because it's changing the medium. So we need to change. We're dealing with a slinky here, yes. So you could change the tension. If you pull it harder, it will increase the velocity. If you had a different type of slinky, so for example, a heavier, or let's just write a change in mass, would also do it. You could have a change in coil size. But notice they're all things about the Slinky that we're changing. It's not about changing the oscillation. Okay. All right. Question 18. Students creating waves in two Slinky springs joined together found that the waves travelled down the first one and were reflected upside down from the junction of the springs. What is the relationship between the heaviness of the two springs? So this is the way to tackle this, is to think about those reflection activities we did in our lab. Now let's draw our two Slinky. But instead, what I'm going to do is actually just going to draw it as a line. So here we have our first Slinky. When it was attached to something fixed, the wave, remember, started off on this side, but then came back 180 degrees out of phase. It was reflected on the other side. But when we had the Slinky and then you had just like a little bit of rope on the end, we found that it came down this side and came back that side. Okay. Think about Newton's third law of motion. For every reaction there's an equal and opposite reaction. Here it is trying to force it up, and so the wall forces the wave down. Here it forces it up, and because there is nothing to force it against, it just ends up bouncing back the same way after it goes up and then back down. So these are our two examples. If it's very fixed and heavy, it's going to reflect down. If it's not very heavy or it's not very fixed, it's going to reflect on the same side. So let's label that for future reference. Fixed, loose. So we're told that it reflects, but it reflects upside down. So from this we could state that the second spring is heavier. Okay, let's have a look at the next part of the question. Will waves be transmitted into the second spring, and if so, will they be in phase or out of phase? Okay, so do we expect it to move in? Yes, we will get waves moving into it. Just because some of it is reflecting back doesn't mean that it's going to just stop all of a sudden. Will it go in phase or out of phase? It will be in phase. So because it's, if we look at this example for a second, yep, it pulls it up and some of it doesn't get transmitted and comes back, but still the rest continues to move it forward. Just because it's a Slinky that's flicking this end up compared to a hand that's flicking that end up doesn't actually change the shape of the wave. It doesn't care. So it will be yes and in phase. Remember, in phase meaning on the same side. Okay, question 19. Now this one's a topic that we haven't really touched here, the idea of a standing wave. It's not something we explore too much in the current year that we're in. It may be depending on what year you're actually looking at this topic. So what is a standing wave? A standing wave is when the wavelength, or half the wavelength to be more precise, is some multiple of the, or some factor of the length of the Slinky. So if the Slinky, for example, is 10 meters long, then if half the wavelength was 10 meters long, then we would get a standing wave, and it would kind of go, let's do that in red instead. It would kind of go up and down like this, like a skipping rope. A skipping rope is an example of a standing wave. If it was a full wavelength, so the wavelength was 10 meters, it would go more like this, and then on the second half of it, it would go like this. And so this bit would go up and down, this bit would go up and down, this bit wouldn't move in the middle. If it was 3 half wavelengths, then we would go up and then down, then up again. You could have a look in the textbook for some pictures of this. So if we want a standing wave, then the length, and we'll give it the symbol L, so L must equal half the wavelength times some number. It could be 1, could be 2, could be 10, doesn't matter what. Okay, but it has to be a half multiple of the wavelength. If it is, then we can get a standing wave existing. Okay, let's move on. Question 20. So, question 20. Two identical waves are created from either end of a long spring. Each wave has a wavelength of 20 centimeters and an amplitude of 10 centimeters. This produces a standing wave pattern. What is the maximum displacement of the resultant waveform as they pass through one another? Well, when we're talking about displacement here, we're talking about, well, what is the size of the wave as it moves away from it? So, if we have our before, and we're told that this is 10 centimeters plus another wave going that way, we're told that's 10 centimeters. Well, if we think of question 6, the stuff that we did before, we would see that would just be a bigger wave with a size of 20 centimeters. And indeed, the book confirms that amplitude equals 20 centimeters in this case. Okay. Part B is asking, well, how far apart are the nodes? Again, this is some more language about standing waves we haven't actually seen. Now, the nodes are these points here, where there is no movement on the wave. So for the blue one, that's a node. For the red one, those two are nodes. The blue one, those two are nodes as well. If there was, say, another set like this, where 1, 2, 3, this would be a node, and this would be a node as well. So nodes are points of no movement. And we're asked, well, how far apart are the nodes on the line? Okay. So all we know is that there is a long spring. We know that the wavelength is 20 centimeters, and we have two waves that can fit on it, and an amplitude of 10 centimeters. So if we've got two waves, and they are, and their wavelength is 20 centimeters, and they are a certain distance away from each other, let's draw that out. We've got our line that things are on, and we've got our, that's the best way to draw this. Two waves. Now, the waves are continually passing through each other and then leaving each other on the other side. So we would end up looking something like, let's see. This one's actually doing my head in. I will do a second video just for this question. Okay, so we will come back to 20b on another video. I will just double check my work solution for that because I don't think what I've done is right. Okay, let's head on to question 21. Two weekend anglers find that their 4-meter boat bobs up and down 3 times in 20 seconds, and exactly 3 wave crests can fit under the boat at any one time. What is the velocity of the waves? Okay, so let's draw a wave, couple of waves. So 1, 2, 3. There's our 3 wave crests, and we can draw our boat. It's not a particularly good looking boat, but there's our boat. And now we've got exactly 1 wave crest, 2 wave crests, 3 wave crests underneath. Alright, and let's see, we're told that that is 4 meters long. Now the 3 times in 20 seconds. Okay, so it takes 20 seconds for 3 vibrations, or if we wanted to work out hertz, we need per 1 second, so we're going to need 3 divided by 20, which would give us, well, let's leave it as a fraction actually, because it would be some disgusting number. Actually, it'd be 0.15, nice and easy, 0.15 hertz. And we need to know a wavelength, because we want to know, well, how fast is the are the waves. So V equals not sure. So we need lambda for this, and we can see, well, if it's 4 meters and there are 2 wave crests, then that must be that the wavelength is 2 meters. Okay? If we make a formula, V equals F lambda, 0.15 times 2 equals 0.3 meters per second, which is what the textbook gives us, though I have lost a little bit of precision there, so maybe they mean that it's exactly 4 meters, so we could say 4.0, which means that this would be 2.0, and so this would be 0.30. Okay, 22. When a tune-in fork is hit, it vibrates at the rate of 300 vibrations per second. Okay, that per second is telling us the frequency. If the speed of sound in air is 340 meters per second, calculate the wavelength of the sound waves produced. Okay, it's fairly straightforward. F equals 300 hertz. V equals 340 meters per second. And we want to know, well, what is lambda? Okay, so V equals F lambda. Lambda will equal V over F. Equals 340 divided by 300, which is the same as 34 divided by 3, which would be 11.3 meters. No, sorry. 3.4 divided by 3, which would be 1.13 meters. Got my decimals wrong. So let's see. We're given 3 units of precision for both of our numbers, so we can keep 3 units of precision here. The book only goes to 2, so they've actually cut off 1, but we do have reason to keep 3. Okay, question 23. Okay, AM radio stations transmit radio waves that are electromagnetic waves similar to light waves, but have frequency from around 500 kilohertz to 30 megahertz. If they travel at 3 times 10 to the 8 meters per second, what is the wavelength of radio waves? So we've actually got to find out 2 numbers. We need to know what is the wavelength at 500 kilohertz and what is the wavelength at 30 kilohertz at the other end of the spectrum. So let's list these out. We've got F1 equals 500 kilohertz, or 500 times 10 to the 3 hertz, and we've got F2 equals 30 megahertz, equals 30 times 10 to the 6 hertz. We are reminded that velocity for light is 3 times 10 to the 8. We could put 3.0 because we've had that earlier definition before. And in this case we want to know, well, what is lambda 1 and what is lambda 2? Okay, so we've just had this formula before, so let's jump straight to that. Lambda equals V over F1 equals 3 times 10 to the 8 divided by 500 times 10 to the 3. Now if we do some check steps there, we can see, well, that's going to be 5 times 10 to the 5, so we should have 3 over 5 times 10 to the positive 3, so it should be around times 10 to the positive 2. So always double check or think your way through the question or the math before you chuck it in, just to help with your check step. And we see that that is dead on 600, or 6 times 10 to the 2 meters. Alright, second one, lambda 2 equals V over F2 equals 3 times 10 to the 8 over 30 times 10 to the 6. So this would be, all this one we can do by hand. We're going to have 10 to the 8 over 10 to the 6 would be 10 to the 2. That's going to make that 10 to the 7, so it'll be 10 to the 1. 3 divided by 3 is 1. So it's just going to be 1 times 10 to the 1, or 10 meters, just to make it simple. So when frequency is small, or smaller, we see that wavelength is a lot bigger, and that's what we should expect to see. So that's good. Finally, question 24. Okay. If we were to put this in a sentence, actually, sorry, for 23, we could say that wavelength is 600 meters to 10 meters. Always good to sort of interpret your results. 24. The speed of sound in salt water is 1,450 meters per second and 340 meters per second in air. Okay, so sound changes speed depending on what we're in. If the frequency of the sound being generated by a motorboat engine is 550 Hertz, what is the wavelength of the sound in air? The frequency of the sound in salt water, the wavelength of the sound in salt water. Okay, so we've got a bunch of things we need to work out here. Let's firstly identify our values. We've got V in salt water equals 1,450 meters per second. We've got that V in air equals 340 meters per second. We have that the frequency is 550 Hertz. Now, it's similar to this in that we've got two of one particular number and we need to work out a couple of other numbers. So A wants the wavelength in air. Okay, we saw that wavelength is this formula, is the V in air divided by frequency. So 340 divided by 550 gives me 6.2 times 10 to the negative 1 meters. Okay, so about 62 centimeters. Alright, let's go on to B. It's asking us, well, what is the frequency of the sound in salt water? Now, some people might be tempted to go, oh, okay, well, I need to use this wavelength and this other velocity to work out this different frequency. No, it's the same frequency. Frequency is just 550. Okay? So the motor is running independent of where it is. It's producing sound into the air, it's producing sound into the water. The frequency is still 550 Hertz. Okay, question C for this is, what is the wavelength of sound in salt water? Now it's exactly the same as part A. So lambda in water equals velocity in water divided by frequency equals 1450 divided by 550 equals 1450 divided by 550, 2.64. Let's round it off as 2.64 meters. Okay, so there we go. It's a lot bigger in this case, just because of how fast it's actually going. Yep. Okay, now there was a question 32. So question 32 is also a one-star question, so we'll put that one in here as well. 32. Okay, we've got a figure below it. It shows a wave of frequency 10 Hertz at an instant in time. So when we can't label the frequency on here, so let's just write that down. F equals 10 Hertz. The wave is travelling to the right, so we're talking about direction of motion. What is the wavelength of the wave? So having a look at the x-axis, we see that we've got distance in meters, and we've got a y-axis of displacement in meters as well. This one looks pretty simple to draw, so let's draw this one out. We have down, up, down, so that's at 1, that's at 2, 3, 4, 5, this is distance in meters, this is displacement in meters. Okay, so what is the wavelength? Well, we just need the distance between, say, crests. So if it starts at 0, our next crest is at 4, well then our wavelength is 4. So A is 4 meters per lambda. Okay, what is the speed of the wave? Well, we've got frequency from the question and we've just worked out wavelength. Well, now we know, well, velocity equals F lambda equals 10 times 4 equals 40 meters per second. Okay, let's keep going. So the next part of the question is, using the letters shown, name any 2 points on the wave that are in phase. Okay, so let's label those. We've got A, B, C, D, E, F. Now, before this, we've sort of used in phase to say it's on the same side, and we can still do that, but it's also got to be doing the same thing. So if we have a look at that, we see that A and E are both at peaks, and they are both about to go down the wave. So A and E are in phase. A couple of other ones in there, if we have a look at that, well, B and F are also in phase. There's nothing in phase with C because there's no point down here. We would probably have that as G. It can be tempting to say, oh yeah, B, D and F, but D is in the middle and going up, while B and F are at the middle and on their way down. So B and F are in phase. Okay, D, if a reflecting barrier is placed at F, sketch on an appropriate diagram the shape of the reflected wave. So what would it look like if it was to be reflected? So let's do that as well. Let's just draw it over the top. So the reflection would be like this. Okay, so if it was about to pull up, it would get pushed down. If we treated that as a barrier, if it was reflecting in phase, then it would just be the same shape as the original wave. It's kind of not clear on what type of reflecting barrier it's talking about. Okay, so that's all the 1-star questions. If you want the 2-star questions, have a look earlier on another video, and if you are looking specifically for, I believe it was 20B, there will be a separate video for that. Thanks, guys.